Okay, sound check, sound check. I can hear myself just fine. Let's try video check. I don't know how much we're going to use the document camera today. I mean, we'll use it a little, I'm sure, but yeah, looks like everything is working there. Okay, perfect. Let me go ahead and unplug these headphones. And let's see what we've got. I'm sure there will be a long pause at some point because there will be something that I forgot to open up beforehand, knowing me, but we'll cross that bridge once we get to it. So today, I'm hoping it's going to be a short one, but knowing my tendency to maybe be a little too thorough in explaining things, maybe it'll be the same length as the typical stream. We'll see. My hopeful estimate is an hour or less, but watch it be like 2 hours or more. So today I just wanted to kind of go over just some general information about the AP exam, some skills that you will want to have mastered that I didn't explicitly cover in the rest of the course, things like that. Oh, I'm already remembering something I forgot to open up. Hold on, let me see if I can find it. I think it's linked in my course plan. At least it better be. Let me see here. So, it's not linked in here. Okay, what I will probably do then is post a link to it in the description if I can find the original link again. If not, then where did I keep it? It might be like a PDF file. If it's not on this computer, it might be on the other computer. Okay, here goes nothing. Let me search. It's not in there, and it's not in that folder, and it's not in that folder. Yep, definitely not there. Maybe it's just in my general physics folder. Nope, nothing in there. What a great way to start off a stream. Okay, yeah, it's not here. It's probably gonna be on my other computer if I have it saved. If I don't have it saved onto a computer, I'm gonna have to see if I can find it again through a random Google search. What are the odds of that? Oh well, for now, let me just make a note of it over here. And that way we can talk about it when it becomes relevant. All right, there we go. That's about as good as it's gonna get for now. Close that folder, open that up. I don't think I need you today, but we'll have you open just in case. Okay, so the AP exam. So I guess first thing I want to do is just go over the overall exam format. They have changed it this year compared to previous years, but I don't think it's that drastic of a change if you ask me. If anything, they're making it a little bit easier. So don't panic. I've seen a lot of people online posting how they're so worried about the format changes, but no format change is going to change the fact that gravity makes things go down and that things that go around in a circle require some sort of center-seeking force and all that. The laws of physics don't change just because College Board changes the way they want to ask you about them. As long as you know your physics, you should be fine. Just read the instructions of the exam carefully and make sure to follow those instructions. You know, when the instructions say draw a force diagram and don't draw components, listen to them and don't draw components on the diagram that you turn in. If you need a drawing with components, draw that somewhere off to the side separately. Things like that, I don't think you need to worry about it that much, but let me go ahead and pull up where you would even find these. So if you just Google AP Physics 1 and AP Physics C, let's do Physics 1 for now, then you should find the course showing up on two different links, actually. There's two different College Board websites that will show up for you in a Google search. One of them is the apstudents.collegeboard.org, and the other one is apcentral.collegeboard.org. You want the AP Central one. This is on AP Central. It's going to look like this. If you get the wrong one, if you get AP Students instead, that one looks like this. You do not want this. This isn't going to have the information that you need. Over here on AP Central, there's a number of things you can look at if you want a comparison between what the course was like before the recent changes and how it is after. There's the course and exam description. You can read this to figure out what's in the course and what's not. I would assume many of you have already seen this and looked through it. It's a long document, but if you really want to read the fine print, be my guest. And it's got a bunch of resources over here and explains some things, gives you a couple of interesting pieces of information. Here it gives you the course weighting. I would hope that none of you care about this because you've learned your physics well enough that you're good no matter what the distribution is here. You should just know all of these, regardless of which one is the biggest percentage. But I guess for those of you taking the shotgun approach and waiting until the last possible week to study anything in the course, I guess your biggest targets would be Units 2 and 3, since they seem to represent the majority of the exam. But don't be like that. Try to actually learn stuff. Anyway, I want to go to this tab over here, titled The Exam. And under the exam, you're going to find a couple of things. You've got the exam overview. Over here is a nice link. It'll take you to a sample booklet if you want to just preview what the booklet is going to look like. This is where you're going to be writing your answers for free response. For multiple choice, you're just going to have a regular Scantron, in case you've never done an AP exam with multiple choice before. It's just going to be one of those bubble sheets. You've seen them before. You've done different sorts of tests that use those bubble sheets. Let's go ahead and close that. There's another link to the course description in case you didn't have enough links to the course description. And then over here, the exam format. So this year, they've changed it to 40 questions in 80 minutes. They've actually done this for all of the AP Physics courses. Now all of them are 40 questions in 80 minutes. It used to be, what was it? I think it used to be 50 questions in, I'm forgetting how much time, but now it's down to 40. I think it was 50 questions in 80 minutes. Or 50 in 75, and now it's down to 40 in 80 minutes. So overall, you have more time compared to previous years. Also, they've changed the weighting. The multiple choice for the AP exams generally used to be a little bit more than 50%. of the total exam score. Now it's completely even. It's 50% multiple choice, 50% of your score is going to be the free response. Also, the free response used to be 5 questions for AP Physics 1 and 2. Now it's down to 4. For AP Physics C, it used to be 3 questions. Now it's up to 4. And it used to be you had about 15 minutes per question. Now you've got 100 minutes for 4 questions. That's 25 minutes per question. And over here, I don't like the terminology they used here, but the translation, if you look at the course description, they're going to have like a sample exam, and it'll show you under each of these 4 headings an example of a free response question that fits these descriptions. Mathematical routines, basically, it's going to be something where you do some algebra and get some sort of solution, or maybe an expression of some sort. Translation between representations, this just means, do you know how to translate back and forth between like a graph and a diagram and an equation? Do you know how to move back and forth between those? Do you know how to connect those things? We've done all that before. Experimental design and analysis, this isn't really something we got to do during the course, but basically the way these questions will work is they're basically labs. So you'll get this question, it'll either tell you to design an experiment used to determine something that you're trying to measure, and you're going to need to know your physics equipment for that stuff. So if you don't know what kinds of common equipment is used in physics, if you don't know the names of all the tools, if you don't know, I had a student last year who had never heard of a caliper before. A caliper is just something that you use to measure the diameter of things. If you don't know what all those common pieces of lab equipment are, what their names are, and what they do, then that is something that you're going to want to study. Make sure you know what those things are. Make sure you know what a caliper is. Make sure you understand how things like a 3-arm balance works. Make sure you understand what photo gate sensors are and what they can measure, things like that. And once you know that stuff, they can ask you things like, again, design an experiment that could be used to determine something. And the strategy there is, of course, you're going to want to know your concepts really well, and you're probably going to want to start with one of your known equations. And whatever the variables are in those equations, that will tell you what kind of equipment you need. If I decide I want to measure something using time and distance, for example, maybe I'm trying to determine the acceleration due to gravity, and I want to do an experiment where I measure the time it takes for something to fall and the distance that it falls, then obviously I'm going to need a ruler to measure distance and a stopwatch or a photo gate sensor to determine the time that an object lands. Things like that. Now, the analysis part is also important. Sometimes you don't even have to design the experiment. Sometimes they'll just tell you a bunch of students did an experiment and it describes the steps that they take, and then it'll tell you something like, oh, the students made the assumption that the reason their calculated value was less than the value that their equation gives is because of air resistance. Explain whether or not you agree with that. And you're going to want to go into detail, explain why you think they're right or wrong, and if you think they're wrong, offer an alternative explanation. This is really just, do you understand your physics concepts? And also, do you have decent writing skills? Reading and writing skills are important. This may not be the AP English exam, but your English is going to matter here. It's going to matter a lot. And then qualitative and quantitative translation. I mean, the quantitative we've been working with all throughout the course, just using your equations and being able to see, which values are bigger when other values change. You know, how does the force on something change when you change the mass or the acceleration? Things like that. The qualitative analysis, on the other hand, it's going to be stuff that's a little bit less mathematical. It's going to be stuff like, let me think, what's an example off the top of my head here? Like understanding, for example, if you have a graph, if you have like a motion graph for something, understanding that if it's like a velocity versus time graph, understanding that it's going to shift downwards if you introduce air resistance. If they tell you this is the velocity versus time graph for an object that's moving under the assumption of no air resistance, they would want you to qualitatively understand, you know, if air resistance is present or friction or whatever. They would expect you to understand that whatever the new graph is, even if you don't know exactly what it's going to look like, you do know it's going to have the velocity shifted lower than it is on the original graph that assumes the absence of friction or air resistance. Stuff like that. And again, if you want like a clear-cut example of each of these 4 categories, just go to the course description. Go to the course description, and towards the bottom of the course description is a sample exam. It's not going to have a full set of multiple choice questions, sadly. It's like, I don't know, I think it was like 10 of them or something like that. But if you go down there, in fact, let me open it up. And let's see if we can skip down to, yeah, here we go, sample exam questions. Okay, so there's the multiple choice. Let's see, how many do they have? Oh, more than 10. How generous of them. Okay, so you have 15 examples of multiple choice questions, and these come with answer keys, by the way, if you want to look at them. But yeah, over here, so notice this should look familiar. First free response question, this is an example of a mathematical routines question. Here we've got a translation between representations question, and we were looking for, and there's an experimental design and analysis question, and last one should be, yes, a qualitative and or quantitative translation question. So let's see, what do they have here? Block 1 of mass m1 slides to the right along a horizontal surface with speed v0. Let me zoom this in so it's easier to read. Toward block 2 of mass m2, which is initially at rest as shown in figure 1. When block 1 collides with block 2, the blocks stick together. Friction between the blocks and the surface is negligible. If block 2 is much less massive than block 1, that is, m2 is this double less than sign, means much less than, estimate the approximate speed of the two-block system after the collision in terms of v0. Justify your estimate using qualitative reasoning beyond referencing equations. So they're telling you here, don't rely on equations. Try to explain in words what your reasoning is. Justify usually means you explain how you know in words or using equations. Here they're specifically telling you beyond referencing equations. Don't rely on equations. But yeah, this is an example of a qualitative analysis. You're not actually calculating anything, but you are demonstrating your understanding that, you know, if something is really large, how does it affect the things? Oh, and I see we have a chatter. Oh, well, glad you're enjoying it. I mean, you missed the entire series up to this point, but that's okay because I have it all in a playlist. This is just a sort of final overview to wrap things up. feel free to ask questions. I don't know if I'll get around to them, but better to have them, and maybe I'll look at them later if we don't have time to get to them today, and maybe I'll respond in a separate video if need be. Let me think. Where was I? Oh, cramming for the exam in 10 days. I just finished talking about that a few minutes ago. Not really the best place to be in, but if you rewind back to a few minutes ago, I was looking at like the breakdown of like the exam weighting of all the different topics. I mean, I would still go in order. You know, learn your kinematics before force, learn force before energy. I guess people will disagree on the order in which you want to do things, but I go in the order that I go for a reason, so maybe look through all the previous streams and just kind of, based off of that, figure out where you want to start. If you're already comfortable with some of the topics, then you can skip ahead to whatever the earliest topic is that you need to work on a little bit more. And yeah, I would just take it from there. I would say, rather than taking the shotgun approach of trying to learn a little bit of every chapter, I think it's better to just focus on some specific chapters. The most important chapters, at least based on my personal opinion and my experience, I would say force is probably the most important chapter, not just in mechanics, but in all of physics, if you ask me. Some people might argue for energy. And the second big one for me would be rotational dynamics. I think if you set the goal to master those without skipping the necessary stuff leading up to them, I think if you really just make sure you understand those two chapters as much as possible, I think that will net you the best results, at least as far as learning physics is concerned. As far as the exam is concerned, well, the strategies adopted for acing exams aren't the same strategies that necessarily work for learning the material well, and vice versa. I never really do teach to the test. I just kind of teach the material as thoroughly as I can, and the natural consequence of that is most people do better on their tests. But I never promise people an A on the test or anything like that. I teach the physics for the sake of physics. Anyway, let me see where I wanted to go from here. So we've talked about the 4 different categories of free response questions that they will ask. Oh, right, under the exam tab. And let me see, I think that is everything. Oh, yeah, and here's a link where you can go and practice for any digital AP exams that you're doing. I'm pretty sure the multiple choice is gonna be on a computer, right? For physics. Physics is one of the courses that's part computer and part paper. And you can scroll down to here to look for exam questions. So a little bit of a warning for the Physics 1 students. The Physics C students, you don't have to worry about this too much once you're on your page. But for the Physics 1 students, this year they have added fluids to the course, and fluids used to be in AP Physics 2. So if you want past free response questions for the topic of fluids specifically, you're going to want to go to the AP Physics 2 page and look at their past exam questions, and you're going to have to sift through these over here. You're going to have to look through them and, you know, download each and every one of these and then read them and skip the ones that are clearly not from the fluids topic. And yeah, that's the best you're going to be able to get as far as fluids practice. You're going to have to just comb through the Physics 2 exams. Also, with these Physics 1 exams, Physics 1 used to include electricity, a little bit of circuits, and also vibrations and waves. Those are no longer part of the Physics 1 course. So if you're looking at some of these older Physics 1 exams, 2015, 2016, 2017, I think it might have been 2018 where they moved electricity out of it. I don't remember off the top of my head, but if you see those electricity questions, or you see like sound or vibrations and waves, skip that stuff. Don't worry about it. It's not going to be on your test. And I think that is it for the Physics 1 exam overview. Let's move on to Physics C, Mechanics. I don't think there's going to be that much left to say here that I haven't said already for the Physics 1 students. You guys are getting the same format of 40 questions in 80 minutes and 4 questions in 100 minutes for multiple choice and free response respectively. And yeah, so you guys went up from 3 questions in 45 minutes to 4 questions in 100 minutes. So you got 1 more question than you usually get, but also you get more time per question. So overall, I would expect it to be a little bit easier than previous years, but we will see. We will see how it goes. Other than that, there isn't that much change. If you go to the past exams, you guys get past exams all the way down to 1999. Wait. Oh, 1999 is all questions, not just the free response. Is that right? Wait, what? Okay, yeah. Hold on. This might be new. Is it a full test? No, it's just the free response. Okay. That's disappointing. I got baited. I don't know why they called it all questions then. But yeah, just look at these questions. I know it's kind of a bummer that you don't get a lot of multiple choice. They don't like to release those. You can get those from your AP teachers if you aren't enrolled in an AP course. Whatever school you are supposed to go take your exam with, they should have somebody there who is the AP coordinator. They might be under a different job title. You'll just have to call the school and ask for who's the AP person, and they will get you your code for AP Classroom where you can practice some of that multiple choice stuff. But you cannot download any multiple choice questions from here, except, well, I think there are a few free ones, but I don't remember how to find them. Anyway, whether you're Physics 1 or Physics C, you're going to want to look at these as well, not just the questions. You're also going to want to download the scoring guidelines over here. Scoring guidelines are more than just a solution manual. Scoring guidelines offer very important information that will help inform your strategy when you're in the exam trying to decide whether to skip a question or not. And even then, how hard do you skip the question? Let's see if I can find an example here. This is going to be kind of luck of the draw, but notice how they give like a breakdown of the points. So this first question, part A, says for indicating speed as the time derivative of position. Just saying v equals dx dt, that gets you 1 point. This is such an easy and cheap point. I'm pretty sure it's actually on the formula sheet. Literally just dump something that I believe is on the formula sheet. Where is it? Is that the formula sheet for Physics C? Yeah. Okay, Physics C, formula sheet. Where is it? Does it say v equals dx dt? No, it does have it for angular speed over here, but it doesn't have it for regular velocity. I mean, knowing that v equals dx dt should be trivial enough anyway. But yeah, my point is, where did we go? My point is, sometimes just saying the one thing that you do know, if you have no clue how to solve a problem, just put down that you know something about the problem. Show them that you understand something. Like, the graders mentality is, please, I'm begging you, show me that you learned something this year. So, write it down. I saw one, I don't remember off the top of my head which one it was, but there was an old AP exam question where you got a point just for saying that energy is conserved. You didn't even have to prove that energy was conserved. All you had to do was recognize that energy is conserved, and you got a free point just for that. So if you have no clue how to do a problem, write down what you do know. Write down something meaningful that you do know, and you'll get a feel for what's considered meaningful if you just read a lot of these. If you read a lot of these scoring guideline sheets, you'll start to get a sense. You'll start to understand the psychology of the graders and what they're looking for, and you'll start to get an idea of what might be worth writing down. And then, let's see, 1 point for taking the correct derivative. If you know how to do a derivative, there you go. That's another pretty easy point. And then if you forgot how to do the third step, fine. You still got 2 out of 3 points. That's good. You don't need that many points to get a 5 on the AP exam. Not as many points as you might think. That being said, I would still try to get as many points as I can. I would still try to aim for 100%, even if it's not very practical or possible for most people, because, you know, even if you know your physics really well, you might miss a negative sign here or there, mistakes happen. I'm pretty certain I didn't get 100% on my AP Physics exam, despite getting a 5 back when I took it many, many years ago. But still, you should aim for the top. You should try to get as much as you can, because at the end of the day, you don't know what the cutoff score is, and anybody who tells you that they do know is lying. I'm probably going to have a little bit of a rant about that later. Well, maybe not a rant. We'll see. It could turn into a rant if I get passionate enough. What else do I want to say about these scoring guidelines? They do have, if you have more than one way to solve a problem, they recognize that, they acknowledge that. If you get the right answer and you know what you're doing and you didn't just coincidentally stumble your way into the correct solution using the wrong approach, you can still get credit even if it's not the main solution method that most people came up with. If you have an alternative way of finding the solution to a problem, they do acknowledge that. They will acknowledge that. So don't fret too much over all the different solution methods that could exist for a problem. Some of these problems do indeed have more than one path to a solution. Anything else over here? Here's another one. For a statement that the work done by the box is equal to the integral of power over time. So even if you don't really know how to do the calculus afterward, if you just set up the calculus, you get 1 point for that. If you put in the correct expression, you get a point for that. So that's another point for setting up the calculus. And if you don't know how to do the calculus in the end, you've already scored 2 points. Now, there was something I forgot to comment on. What was it? Sometimes you will get the points for getting the correct result, even if you don't know how to actually calculate the correct result. Like, if you know that for example, when the mass of something doubles, then the force quadruples, but you can't explain mathematically why, you might still get credit for that, but you will see once you read these scoring guidelines, I don't know if there's an example of it in this one in particular, but you will sometimes see they will state, that you get the point for getting the right answer without showing the work. Other times they will say no points are credited if you got the correct solution without doing whatever it is they asked you in the previous part. That's something that you'll see if you read more and more of these scoring guidelines. So read them, read them, read them. Make sure you download these. They're not just a solution manual. They are so much more. And if you want to look at some sample responses, how other students did on this exam, you're more than welcome to. But really, it's just the questions themselves and the scoring guidelines. Those are the two big things that you want when you're downloading FRQs. The scoring statistics and grade distributions, they used to give really, really good statistics, but they don't share those statistics anymore. Now it's just, okay, here's the number of people who, what is this? This is the breakdown per question. So question 1, on average, people scored 9.8 out of 15 points with a standard deviation of 3.64. I guess this helps you assess how hard the question was. So it looks like question 3 was the hardest for that year. So maybe that's a sign you should prioritize it. But I don't think this is going to be that much value. Then there's the grade distributions. This used to be a lot more detailed, but unfortunately not anymore. There used to be, like, especially for the multiple choice, they would share this breakdown of here are the people who scored 1s, 2s, 3s, 4s, and 5s, and then here's the percentages of each of those groups that answered this question correctly. So you would see, like, multiple choice question 14. Of the people who scored 5s, only 48% of the people who scored 5s got question 14 correctly. And that tells you, oh, even the people who got 5s, half of them, more than half of them, didn't get this question right. So maybe this is something worth studying and understanding. But yeah, unfortunately, they don't have that information anymore. Now it's just very, very surface level statistics. Is using 10 as the value for gravity viable for the exam? Yes, it is. That was one of the things in my notes that I was going to bring up. Yes, using 10 is acceptable. Sometimes on the multiple choice, you will see, based on the answer choices, you'll be able to tell, if you see multiples of 9.8 versus multiples of 10, you'll be able to see just looking at the answer choices which one they used. They kind of flip-flop back and forth between using 9.8 and 10. But if you still use 10 anyway for all of them, then if the answer choices were calculated using 9.8, you'll know to just pick the one that's closest to what you got using 10. Assuming you did everything else correctly, that is. If you use 10 and you get 5 and the answer choices don't have a 5, but one of them is 4.9, that's the one. So yes, you can get away with using 10 for G. What I would recommend is just don't even plug in the value of G. Just save it until the very, very end and then look at your answer choices and see whether they are based off of 10 or 9.8. So those are your solutions for the G problem. But yes, using 10 for G is something you can generally get away with. Unless, of course, they explicitly say, using G equals 9.8. Or if you're on another planet where G is going to be very different from 9.8. Anyway, so that's scoring guidelines and using them. And those are the scoring statistics if you want to look at them. And I think that is it for exam format and finding past exams. Now let's go ahead and talk about multiple choice questions. So let me go ahead and switch over to my document camera and let's see what we can say about multiple choice questions. So I'm just going to talk about different types of multiple choice questions that you'll see. Just some common types that I've seen over and over and over again. One common type is going to be choose the correct graph. Choose the correct graph. And your answer choices, they're going to be A and B and C and D. By the way, another thing that they've changed for this year is instead of 5 choices, now it's only 4 choices for the multiple choice. It used to be A through E, now it's A through D. But yeah, they'll have, a bunch of different graphs. And sometimes these graphs will be for more than one question. But yeah, they'll draw a bunch of different graphs over here for you, and they'll ask you to choose which graph answers the question best. And again, they might use this for more than one question, like maybe questions 12 through 14 all are going to be based on these 4. And question 12 will be like, which of these graphs is a good graph of position versus time to describe the motion of an object that, I don't know, moves at constant velocity, which I guess is none of these, actually. But if that was the question, you would pick the one where the graph is just a horizontal line. Pretty simple stuff, really, if you just know what your physics quantities are and how they relate to each other on a graph. We've seen all that before. So choose the graph, that's one of them. Choose the correct expression is another one. Choose the correct expression. Choose the expression. Sometimes you're not going to be asked to calculate a number. Sometimes you're going to be asked to get an expression. I've talked about these expression problems and questions numerous times throughout the course. We should be very familiar with this if you've been following along with the course since the beginning, but they might ask you a question like, choose the correct expression for the velocity of an object that's dropped from rest from a height h. And there will be a bunch of different choices, and the one that you will pick will be the one that says v equals, you should get square root of 2gh once your math is all done, once your algebra is all done. So you're not going to actually get a number. You're going to get some sort of expression, and then over here they might have like 2gh without the square root, and they might give you something like v squared over 2g. Actually, no, that wouldn't be right. Maybe h squared over 2g. They'll give you 4 different expressions, and you'll have to pick the right one. Nothing too foreign for most of you, I would assume. And yeah, here it is in my notes. It was asked earlier, you can use 10 as an approximation for g, just in case you didn't hear me the first time. Another common type of question, let me get a new sheet out here. Another common type of question is, find the units of a constant or variable. They might give you something like, they might give you a familiar quantity, or they might give you a completely unfamiliar quantity. Like they might give you, in Newton's law of universal gravitation, force of gravity is big G times m1 times m2 over r squared, d squared, whatever you want to call it. And they might ask you, find the units of g, and then your answer choices, of course, will be whatever they are. And we've done a number of these before. I've shown these quite a few times throughout the course. I think we specifically did this one for g, but if you're looking for the units of big G, you would just do force units are going to be newtons, and then the units of G, we'll just put G in brackets for now to mean units of G, mass and mass. Those are kilograms times kilograms, so that's kilograms squared over distance squared. Those are going to be in units of meters squared typically, and then you multiply the meters squared and divide by the kilograms squared, and you get Newton meters squared per kilogram squared. And then you do all this and you look at the answer choices and oh, none of them say Newton meters squared per kilogram squared. What do I do? Well, you break down the Newton into its base units then. You know your equations that involve force. You know other force equations like, for example, net force equals ma is one such equation you could use. And you know here, net force is going to be measured in newtons, and mass is going to be in kilograms, and acceleration is going to be in meters per second squared. And now you know, oh, a newton is equivalent to a kilogram meter per second squared. And then you substitute that in here, and you simplify and get whatever units you get. And then pick whichever answer choice has the right assembly of units. So that's if they ask you for something from a familiar equation. They might give you something unfamiliar. They might give you something like, what are the units of, say, the ratio? Maybe they ask you, what are the units of the ratio force of gravity over r, for example. Not really anything too new there. You just do the same thing that you did over here, really. Just take whatever the units of this turn out to be, go through the steps if you need to break it down into more base units, and then also take the units of this and just cancel out whatever needs canceling out. Simplify wherever you can. You might see the answer choices written in a slightly different format. It might not be written as a fraction. You might get them written where everything in the denominators is going to be written with negative exponents. So maybe it is Newton meters squared per kilogram squared, but they write it like this: Newton meters squared, and then times kilograms to the -2. I would hope that we know our laws of exponents and that we can easily see that something to a negative exponent means that it's in the denominator. So that might be the way that the answer choices are written. But yeah, there you go. That's the find the units of a constant or variable type of question. Typically you see one, maybe two of these on the AP exam, but usually it'll just be one in my experience if they ask at all. They typically do. They typically ask at least once per year in the multiple choice somewhere. Determining information from a graph, so they give you a graph and then they ask you to determine something. They give you a graph like, here's a momentum versus momentum versus time graph. Whether you're physics 1 or physics C, you should be able to recognize that the rate of change is going to be the slope. Even if you are physics 1, you should be able to know if the graph is a curve like this. You should be able to tell that the slope of the tangent line is changing. It's going from this steep to now it's getting flatter, so you know that the rate of change of momentum with time is a little bit higher here but lower here. You know that it's decreasing, and you should remember the relationship that change in momentum is equal to impulse, which is equal to force times change in time. And then you know that change in momentum over change in time is equal to force. Therefore, you know that the slope of a momentum versus time graph is equivalent to force, and then you can conclude that the force is decreasing here. So that might be what the answer choices are. Determine what's happening to the force on this object as time progresses, and the answer choices will be the force is constant, the force is increasing, the force is decreasing, or nothing is known about the force and nothing can be determined. Probably. That would be my guess as to what the 4 answer choices would be if they gave you something like this. So determining things from a graph. The stuff we've seen before. Change factors and ratios. So this is going to be stuff like, for example, I guess we'll go back to Newton's law of universal gravitation actually is a pretty good example of this. Actually, no, let's do kinetic energy. They might tell you something like the kinetic energy of an object is k0, then its speed is doubled while its mass is tripled. K0, original kinetic energy of some object. And then they say mass is tripled and velocity is doubled. What is the kinetic energy of the object now? And then the answer choices will be it's still k0, it's half of k0, it's, let's see, what would it actually be? If the mass is tripled and the speed is doubled, so kinetic energy is 1/2 mv squared, so k0 is 1/2 m0 v0 squared, and then k nu, or whatever you want to call it, k nu, or maybe you'd like to just call it k star, whatever you want to call it, is going to be 1/2, and then the new mass is 3 m0, and the new speed is 2 v0, and then that squared, and then you pull out all of these new factors. So you pull out the 3 from 3m0, and you pull out, when I square the 2v0, then that becomes 4v0 squared, so I pull out the 4, and then I'm still left with the 1/2 from before, the m0, and the v0 squared, and then you go, oh, this was the original kinetic energy, so this is going to be 12 times k0. Therefore, the correct answer choice is C, 12k0, and probably they'll give you choice D just in case you somehow did it wrong and came up with 1/12. They might also throw you that one, just so you go, oh, it has 12 in it, that one must be right. So yeah, these sort of change factor problems or ratio problems, they might either ask you how does some quantity change if the other quantities it depends on change by a factor of whatever, or they might ask you, what is the ratio of the new quantity to the old one, in which case for this one the answer would be just 12 instead of 12k0. Could be either way. They could ask you like what's the ratio of the two quantities. Actually, what would be more likely if they're asking for a ratio, they might ask for something like you have two planets and they've got like different masses and different radii, and you compare the acceleration due to gravity on their surfaces, and they tell you, planet A will have like a gravitational acceleration that they'll call GA, and then they'll describe planet B in terms of planet A. Planet B has this many times the mass of planet A and this many times the radius of planet A, and they'll ask you, what is the ratio GB to GA, the ratio of the gravitational accelerations on their surfaces? That's basically just another version of this problem. So that is something that you will probably see on the multiple choice. Also, you might see this just in a qualitative sense. They might ask you, if one factor changes, how the other variables change, as in just, will it increase, will it decrease, will it stay the same, will it sometimes increase and sometimes decrease, things like that. What will happen to, what will happen to an object, for example, if it's, let me think. What will happen to the acceleration of an object if it's thrown, I don't know, upward into the sky with a very, very high velocity, and then you take into account how the gravitational pull is decreasing the higher up you go. That might be an example of this type of question. Or it might be just a really simple, straightforward thing like, if you increase the height, what happens to the final kinetic energy of an object dropped from that height? Or if you throw an object from a given height, horizontally versus straight up versus straight down versus just letting it drop, they might ask you which of those results in the highest speed at the end. Another type of question they might ask you is, which of these statements is correct? They might give you a number of statements and ask you which one is correct. They'll give you something like, an object is thrown off the edge of a cliff of height h. Might as well keep going with this example since it's sitting in my head right now. And then they might ask you something like, if you change the initial speed with which this is thrown, which of the following statements is true? And then statement 1 will be that the object will hit the ground sooner. Is it true or false? And then statement 2, the object will hit the ground sooner. And then statement 2 will be something like, the object will still gain the same amount of kinetic energy. The object gains the same amount of kinetic energy compared to when it was thrown at the lower velocity. The object will gain the same kinetic energy and statement 3 might be something like, what can I do? For example, the acceleration of the object is the same as before. They might ask you something like this, and then the answer choices will be like choice A, only statement 1 is correct. Choice B, only statement 2 is correct. Choice C, statements 2 and 3 are correct. Choice D, statements 1 and 3 are correct. And back when we used to have a choice E, maybe there was an option, none of these are correct. That's a type of question that you might see. Other than that, there's just your straightforward questions and your conceptual questions. Things that really should be super trivial and super easy if you understand your concepts. Like, I've seen questions that legitimately test your understanding of Newton's third law. The force that one object exerts on another is F0. What can be said about the force that the other object exerts on the first object? And then the answer choices will be like, it's 2 times F0, it's 1/2 of F0, it's equal to F0, or, it's some other multiple. And that's really just, come on, it's Newton's third law. That one should be trivial and easy, simple conceptual stuff like that. An object is launched as a projectile. The direction of its acceleration is what? Changing as it moves, always down, always up, always down with constant magnitude, always down but decreasing, increasing, whatever. You should know that for a projectile, its acceleration is always straight down and just equal to g. Stuff like that. Stuff that if you hurry, then you're probably going to make a mistake, but it really should be just really easy points for you to get. So that is the overview for multiple choice. Now, what about free response questions? Free response questions. So I've already talked about some of these while we were looking at some of those FRQs earlier, but you're going to have your derive an expression problem. We've done that throughout this course a number of times. You probably have book problems in your textbook that have you deriving an expression. Oh, by the way, speaking of textbooks, I know a lot of people get really passionate about only studying AP questions at this point when the exam is just weeks away. Book problems are still good. Don't underestimate book problems. Obviously, not every single book problem is going to be that good as preparation material for the exam, but there are probably some really good questions in your textbook that are on par, sometimes even more challenging than your typical free response question on the AP exam. So don't completely ignore your textbook. Don't completely ignore your textbook. It might be a source of questions in there. It might have a question or two that are really, really good. Well, probably more than just 2. I mean, I guess it depends on the quality of the book. Not all textbooks are created equal after all. But yeah, don't be scared to practice with material that isn't exactly written and worded the way the AP exam likes to write and word their questions. At the end of the day, it's still physics. Anyway, you've got your derive an expression type of problem. We've seen that. Usually this will be just part of a bigger problem. Usually this will be closer to the start of a free response question, in my experience. They'll give you some information, they'll describe a scenario, and then they'll ask you, derive an expression that could be used to calculate whatever. Usually this is the lead up to some sort of experimental design question, maybe. And then the next part of the question will be, use this expression that you derived to estimate, calculate, whatever. Second type we already talked about, which is experimental design, error analysis, and knowing your equipment. I already talked about the importance of knowing your physics equipment. Look that stuff up if you need to. Make sure you understand what all the different types of equipment are. Oh, also, come to think of it, I forgot to go over the formula sheets. Let me quickly move on to those. So, if you've been doing the course with me up to this point, I expect you to just memorize your equations anyway. There are equations that are not on this sheet that I would expect you to have memorized anyway, not just because they're not on this sheet, but because I think if you don't have them all in your head, it'll hurt your ability to analyze problems. And more than just rote memorization, you know what I've been saying. Make sure you understand where your equations come from. I mean, some equations are a bit difficult to derive, so I understand with those the use of mnemonics and stuff to try and remember them. But a lot of these equations, I don't memorize them so much as I rederive a bunch of them from scratch on the spot, or at the very least, they make intuitive sense to me, and that lessens the dependency on memorization. You know, being able to look through an equation and go, okay, this is velocity, for example. It's equal to some other velocity plus acceleration times time, and you think about acceleration and you go, oh, acceleration is speed units over time units, and if you multiply that by time units, you get more speed units, or velocity units rather. And then a velocity plus a velocity equals another velocity. That makes sense. Being able to go through that thought process and understand why the equation you have in front of you makes sense, especially looking at the units, that helps double check and make sure that you've got the right equation. And it helps commit it to memory. You might also recognize over here, you might be seeing that the equations are formatted a little bit differently from the way I write them. For example, this x minus x0 thing, I usually just write this as delta x. Over here, theta equals theta 0 plus all this stuff, I usually just write theta minus theta 0. The theta 0 is subtracted over to the left-hand side, and I call the whole thing delta theta. My version is delta theta equals, and then just this stuff over here. Let me see if I can zoom this in. Yeah, there we go. So I would just migrate the theta 0 over to the left and call that whole thing delta theta equals omega 0 t plus 1/2 alpha t squared. So yeah, difference due to personal preference. You should be able to adjust quickly when seeing that they're using, you know, a different notation from what you're used to. You should be able to just adjust to that. Speaking of adjusting to things, they like to use K for kinetic energy. I like to call it KE because I feel like that's more intuitive, even if K is faster to write. They also like to use U for potential energy. So if you're used to my way of writing things, just make sure you're aware for the AP exam, they use K and U for kinetic and potential energy. And here's how you know you've got the most up-to-date Physics 1 formula sheet. It's got the pressure and fluids stuff. It's got all those equations, so you know it's the up-to-date one. Yes, it says 2024 there, even though it's the 2025 exam. That's because 2024 is the year of the latest update. So yes, it is the most up-to-date one. For Physics C, your formula sheet, I would hope, for both of you, Physics 1 and Physics C students, I would hope that you don't need any of the information on this first sheet. I would hope that we all know formulas like the volume and surface area of cylinders and circles and spheres. I would hope that nobody needs the equation for the area of a rectangle or a triangle. Otherwise, how did you even get into this class in the first place? Maybe for the students who only knew algebra and didn't have much trig, I can see this over here being helpful, but if you've gotten through the end of this course, you should have had enough practice with sines, cosines, and tangents by now. So yeah, if you see this sheet and it looks useful to you, then that's a sign that you might need to practice a little bit more, because these are things that you should remember. Maybe I would make an exception for these. Physical constants. G equals 9.8. I expect you to know that one. Big G being 6.67 times 10 to the negative 11. I would hope, just due to the sheer amount of practice that you did in the gravitation chapter, that this one stuck in your head. But if not, there it is. So maybe that's like the one thing. Okay, two things, and then one atmospheric pressure. Wow, they're really going easy on you, because it's supposed to be 1.013 times 10 to the 5, but they simplified it to 1.0 times 10 to the 5. Okay, so they're going really easy on you with the definition of standard atmospheric pressure. Good to know. But you're not going to lose points if you use 1.013, by the way. Like, they're not going to grade you too harshly if you round slightly different from them. They're not going to nitpick over significant figures. That's more of an AP chemistry thing, and even the AP chemistry exam is a bit forgiving with significant figures, actually. But yeah, in AP Physics, don't worry about your significant figures too much. As long as you're not doing something really, really absurd, you should be fine. Like, I use 6.673 for Big G. I'm not going to lose points for doing that. They're not going to care about small differences that can be rounded off. As long as the mathematical reasoning is all sound, you're going to get your points. But yeah, that's the overview of the formula sheets. Let's see, what else do they have for you for AP Physics C? They've got, oh wait, that's Physics 1. Physics C, okay, similar information here. Here they've got a little bit of calculus for you. I mean, I showed this in the previous two streams covering the calculus topics. We did glance at this a little bit. But yeah, a lot of your calculus formulas are in here. Do they have, yeah, moment of inertia? They're just straight up giving you that it's the integral of r squared dm. You don't even need to go through the reasoning process for it. They've given you the parallel axis theorem right there. They've given you the period formulas for physical pendulum, mass spring system, and regular pendulum, simple pendulum. And they gave you just one equation, one time function for simple harmonic motion, because if you know your calculus, you should be able to derive the other two really easily. Here, again, a section I hope you don't need. Calculus stuff, if you haven't taken AP Calculus, this might be useful to you, but I would make sure to practice so that you're not very dependent on much of this, if any of it. And then over here, the one thing that's a bit new is they're using this unit vector notation over here for this third equation under vectors and the fifth equation under vectors. I don't know if you're going to see that on the exam. I mean, they've never used it before, and I don't see why they would start now. Especially because none of the other equations seem to be written in a way that alludes to the use of unit vector notation, but I showed you how to deal with it just in case it does show up. So go back to the calculus-based problem streams and look at those. Go back to the past 3 streams for Physics C if you need to look at how to work with this stuff. I still need to timestamp those videos, by the way. I'll work on that sometime during this week, and hopefully by Wednesday, if not sooner, get all of that done. Plus that one mishap from the previous stream that needs to be addressed, maybe, in a comment. We'll see. Anyway, back to the document camera. What was I doing before I went to the formula sheets? Oh, right. We were talking about experimental design and error analysis. So with your error analysis, you're going to want to try and be thorough. Don't just go for the cheapest answer. Like if they give you a question where they give you something like they did an experiment and I don't know, they rotated an object and they found that the speed of the rotation was less than what their equations predicted. Don't just go, oh, it's just because of air resistance. Try to give a more detailed analysis than that. Try to think of other causes. Try to think of, well, maybe it's because the moment of inertia was underestimated. And also be clear about that as well. If something is overestimated versus underestimated, you don't want to just say something was measured inaccurately. You want to indicate, show that you understand in which direction is the inaccuracy. Is it an overestimate or an underestimate, and why? Make sure you're able to explain that stuff. So an object, if it rotates slower, if it rotates at a slower speed than what you were expecting, yeah, maybe air resistance robbed it of speed, or maybe its moment of inertia is, well, if it rotated slower, that would imply that its moment of inertia is actually higher than what they predicted. And then try and see if there was a reason why they measured it lower than it should be. Maybe they assumed something, maybe parts of the object started spreading out farther, increasing the moment of inertia as the object started rotating. Take that into account. Show them that you understand what's going on. Don't just go for the cheap answer of blaming everything on air resistance. Give an actual detailed analysis if they ask you to explain why something was measured wrong. Sketching a graph from an equation or from another graph, that's something that they might ask you to do. Sketching graphs, just knowing the shapes of your graphs is going to be important. They might give you a question like, I don't know, they might give you something like sketch the kinetic energy and potential energy of an object as it moves through different positions. Maybe it's like an object attached to a spring, and you'll have energy in general, and then here's position, and you might have, let me think, I'm thinking of a very specific exam, I don't remember which year it was, where they started with a question where an object was connected to a spring, I believe, and then it was moving on a frictionless surface up to a point, and then after that point, so after a distance d, after that point, it was all friction from there until it came to rest. So it would have started with 0 kinetic energy and maximum potential energy, and then potential energy would have decreased, and you had to try and figure out how that potential energy decreases, and you would have gone potential energy plus kinetic energy equals the total mechanical energy equals E total. Just apply conservation of energy there and go, well, if kinetic energy is 1/2 mv squared, well, v isn't really useful on this graph, so I guess you would use the potential energy for a spring, actually. So you would do 1/2 k x squared plus the kinetic energy equals constant. And then you would, on your graph, you would have to know, start with some sort of total, start with some sort of constant value, and your potential energy would be that. And then you would want a graph that, well, potential energy is going to decrease as x increases. So potential energy would be, let's see, it decreases as x squared. So actually you would want, so potential energy would go to 0 over here. this would be, no, wait. It would go to 0 some point before position D. Actually, hold on. I'm remembering it. So it was an object that was pushed to some negative distance over here. I think they called it like negative lowercase d. It was attached to a spring. Equilibrium position is here. So this is where you'd have 0 potential energy. Here is where it would all be potential energy. Let me draw this graph in green. Here's where it would be all potential energy. Here's where there would be no potential energy. And then after that point, the object detaches from the spring, so there's no more potential energy at that point. And you'd have to graph how does it decrease in potential energy. Does it decrease like this? Does it decrease like this? Or does it decrease in a straight line? Well, it definitely won't be a straight line, considering that it depends on x squared. I would expect it to be some sort of curve. And then based off of that, they wanted you to then graph the kinetic energy as well. So the kinetic energy would be just flipping whatever graph you get for potential energy. So let me see here. Potential energy would be decreasing in what way? As x progresses over here. So it would be, well, it increases from 0 to 1/2 kd squared as you go left to right. So it would be like this. It would be this one. It would have to be this one. It fits the form of f of x equals some constant times x squared, where x is a negative value. If you know what a quadratic graph looks like, which I would hope most of you do, that's how you would figure out what shape your sketched graph would need to have. They would expect you to know a bunch of common graphs. They would expect you to know, what a linear graph looks like. They would expect you to know what a quadratic graph looks like. They would expect you to know what a square root or an exponential function looks like. That's not an exponential, that's a reciprocal. And then an exponential function would look like that if it's a decreasing exponential function, or flip it horizontally or vertically depending on whether the function itself is positive or negative and whether the exponent in the function is positive or negative. But yeah, getting your equations into the format of one of these common graphs, getting your equations into the format of f of x equals, if it's a parabola, it's going to be of the form ax squared plus bx plus c. If it's linear, it's going to be in the form ax plus b, or I guess it would be mx plus b is what you guys are used to. F of x equals mx plus b. F of x equals some multiple maybe times square root of maybe x plus or minus something, and maybe plus or minus one more thing. That would be a square root graph. Just knowing what these functions look like, and x is a placeholder here. It doesn't have to be x. Whatever is on your horizontal axis here, it might be x, it might be t, it might be v, it might be f. Whatever the variable is, just swap that in for x in these and you'll get the format of that function, and then based on its format you'll know what graph shape it's going to go with. It's going to be one of these familiar graphs is the bottom line. So if these graphs are not familiar to you, then maybe crack open your pre-calculus textbook. If you don't have a pre-calculus textbook, go download a free one from OpenStax. Just type OpenStax into Google and go download their pre-calculus textbook and review what you need to review. Anyway, I was doing this problem, so yeah. 1/2 kx squared, its left half is going to look like that, so that's your potential energy, and then kinetic energy would start at 0 and would increase in the exact opposite way. It would mirror this. And you'd have to do a little bit of math to convince yourself that that's true. And then it would stay constant over here while it's moving on the frictionless surface. And then once it reaches this position D, that's where it encounters a rough surface, and you would have to convince yourself, you would have to do the math and show that the change in kinetic energy from this point on is linear, since it's due to a constant force of friction. And it would just go down in a straight line. Getting the shape of the graph right is basically what you'd be getting graded on for this. I feel like this is different from the actual graph of the problem I have in mind. I might be mistaken on some of the details of that question, which wouldn't be surprising. I mean, I wouldn't expect anybody to have the past AP exam questions memorized all that well. I'm just going off of a vague memory of a question that I tend to ask my students every year for practice. Anyway, moving on. A best fit line or best fit curve. So they might ask you these types of questions. I actually have one ready to go here as an example. Where is it? Why are these tabs open? I don't need these. No, not that one. I can close these. We don't need them anymore. Don't need you anymore. Don't need you anymore. Don't need you anymore. Don't need those. Don't need those. Here we go. So let me go ahead and switch screens. Okay, 2005 free response questions. So here's one that I give to my students every single year. It's probably the best example of a best fit line question because it allows me to go over everything. So question 2 of 2005 says, a student is given the set of orbital data for some of the moons of Saturn shown below and is asked to use the data to determine the mass m sub s of Saturn. Assume the orbits of these moons are circular. I hope you remember your gravitation stuff. So part A, write an algebraic expression for the gravitational force between Saturn and one of its moons. You would just use force of gravity equals big G times the mass of Saturn times the mass of one of its moons divided by the distance squared. The distance being the orbital radius, in this case big R. Part B, use your expression from part A and the assumption of circular orbits to derive an equation for the orbital period t of a moon as a function of its orbital radius. So this is something here where they said use your expression from part A, meaning that you can't get credit for this if you didn't do part A. Now, if you did part A and you did it wrong, will you still get credit? I'm not entirely sure. You'll have to check the solution guide for that, because sometimes they will still give you credit for what otherwise would have been right if only you hadn't messed up the previous part. Other times, they're stricter. Other times they go, no, you should have gotten that previous part right. It was easy enough, or whatever justification they have. But when in doubt, if you're not sure how to get the correct expression for the previous part, you might as well just use whatever you can get and try and do the second part if you have the time to spare. Maybe go back to that after doing some of the easier questions, come back to this and put something down. You might get points. I mean, at that point, you might as well take the risk because you have nothing to lose. But anyway, use your expression and the assumption of circular orbits to derive an equation for the orbital period t of a moon as a function of its orbital radius r. So what's nice about this, and a lot of the free response questions do this, is they kind of gradually walk you through the steps leading up to the big thing that they want you to do at the end. So if you try and do the problems, you might have some things where, you know, the answer to part C might be something you derived along the way while solving part B. That's something that can still happen, but generally they're pretty good at the order in which they ask you the questions. They're pretty good with it. So try and trust that, at least if you don't immediately see, you know, something better. You might as well just trust the order in which they're asking their questions. It will probably lead you in the right direction, especially for the later parts. Now let me go ahead and actually do this one. So write an algebraic expression for the gravitational force between Saturn and one of its moons, and then use that expression and the assumption of circular orbits to derive an equation for the orbital period of a moon as a function of its orbital radius. Let's go ahead and actually do this one. So they've got first part A, we would do force of gravity equals big G times the mass of Saturn times the mass of whatever moon is in question divided by the orbital radius squared. So that's part A. Part B, they want you to use this and the assumption of circular motion. So that just means use the gravitational force as a centripetal force. It would be the mass of the moon times v squared of the moon over r is equal to g msm over r squared. Cancel an r. Cancel the m's, so the mass of the moon doesn't even matter. And then what did they want us to do? They wanted us to derive an equation for the orbital period, capital T. Okay, well, I don't have period in this yet, so I guess something is going to have to involve period. Well, period, by definition, is the amount of time it takes to complete one cycle of something. In this case, it's the amount of time to travel a distance of 2 pi r at a speed of v. If you don't know this equation off the top of your head, the way I like to think about it is the speed of something in a circular orbit is equal to the distance traveled in a single cycle, which is 2 pi r, divided by the amount of time it takes to complete a single lap, which by definition is period. And then rearrange this, multiply the t, divide the v, and you end up with this. Actually, I should just have this and plug that in over here. So 2 pi r over t. So I have 2 pi r over big T. That thing squared is equal to g mass of Saturn over r. if I go ahead and square this, I get 4 and pi squared and r squared and t squared. Square every individual thing. Exponents distribute over multiplication and division, but not addition and subtraction, as I would hope we all remember. And then GMS over R. They wanted an equation for orbital period t, so I'm going to get the t squared by itself, multiply it over to the right-hand side, and then move everything else to the left. So we get... I'm going to be skipping some steps here, but you can do it step by step on your own time if you want to. We're going to end up with t squared on the left, or on the right, and on the left we're going to have 4 pi squared over GMS and times r cubed. So this is what we will end up with, and then I guess square root both sides, so you get t equals the square root of this stuff. I'm just going to box this for now, even though it's not exactly the answer they want. Derive an equation for the orbital period t of a moon as a function of its orbital radius r. Yep. So just square root both sides of this, and you're good to go. Next, it's asking us to determine which quantities should be graphed to yield a straight line whose slope could be used to determine Saturn's mass. Which quantities should be graphed to yield a straight line whose slope could be used to determine Saturn's mass? So this is a skill that you get to learn in chemistry, but they don't really spend that much time teaching it to you in physics. They kind of just assume you know, which might be fair considering the math level you have to have in physics. I guess it is kind of fair that they would expect you to know your math well enough to be able to do this. But yeah, figuring out what to graph to get a straight line. So a straight line has the format f of x equals mx plus b. So you've got variable equals some constant times variable plus maybe some other constant. That is what we want to get as a linear graph. We want to get that as a linear graph, and it's supposed to be used to determine Saturn's mass. Now, just because they say that its slope could be used to determine Saturn's mass doesn't mean that it needs to equal Saturn's mass. It can just be a step along the way, which is exactly what we're going to have here. So what I am going to graph is actually going to be t squared versus r cubed, and I will explain why. So let me rewrite it over here since I've got the space for it. I'm going to write t squared is going to be my dependent variable, and then 4 pi squared over GMS. This includes the mass of Saturn, so this is what I want our slope to be. And then r cubed is going to be over here. I guess you could also do, if you really wanted to, you could do t equals, let's see, 2 pi over square root of GMS, and then square root of r cubed is r to the 3/2. This also works. Both of these will work, but this one has all these square roots in it. It's nasty. You don't want to deal with this. Stick with this. It'll make your life easier. But yeah, I want to pattern match this. I want this to match the format of y equals mx plus b. In this case, I don't really have a plus b, but I want to make this match y equals mx plus b. Well, this is the y. The 4 pi squared over GMS, that's the m. And then the r cubed, that's the x. And then the plus b is, well, plus 0. There's nothing there. So my y, quote unquote, my vertical axis is going to be t squared. My horizontal axis is going to be my x, my r cubed. So it's not t versus r, it's t squared versus r cubed that I want to get. And then whatever that graph looks like, the slope of that graph is going to equal 4 pi squared over g times the mass of Saturn. Whatever that slope is, we'll set it equal to this. We will plug in 4 and pi squared and big G and solve for the mass of Saturn. And there you go. The slope doesn't have to be equal to the mass of Saturn up front. It can be equal to some constant that involves the mass of Saturn, and that will be good enough. So now that we have decided on an equation that is in the correct format to give us a linear relationship, let's see what they're asking us next. Complete the data table by calculating the two quantities to be graphed. Label the top of each column, including units. So you see here, they've given you 2 free columns. Sometimes they give you more free columns than you actually need. Sometimes they give you more free columns than you actually need. Like if you went the other approach of, instead of t squared versus r cubed, you could have done t versus r to the 3/2. If you went with the other option, then you would only need one of these columns, and you would actually lose points for filling out more columns than necessary. So make sure you know what information you need and why you need it, and don't waste time on information that you don't need, is the moral of the tale here. So I would graph, or not graph, but in these columns, I would make one column for t squared and another column for r cubed, and then I would just take each of these values. So 8.14 times 10 to the 4, I would square that, and whatever number I get from my calculator, type it in here. 1.18 times 10 to the 5, square it, put it in here. Oh, and by the way, see how they label the units over here? They expect you to do that over here. So if you type it, or not type, if you write t squared in here, what units are those going to be? Those are going to be in units of seconds squared. You need to write that. And then r cubed for our second column, that's going to be in units of meters cubed. So you would write that down. And I think I actually want to write down these numbers. Oh God, we're already approaching 2 hours. I was joking at the beginning today about how long this was going to be. Goodness. Okay, let me grab a new sheet and also switch back to my document camera. Very important. Let me grab a new sheet here and let's actually calculate these values. I actually do want to write down these numbers because there's another important thing that we need to learn from this. So it said 8.14 times 10 to the 4, that's parentheses 8.14 times 10 to the 4, and then I'm going to square that and switch my calculator to scientific mode so that it reports it in scientific notation. So I'm getting 6.625 times 10 to the 9, 6.625 times 10 to the 9, give or take. Oh, 626 actually, since the next number is a 9. Okay, next one is gonna be 1.18 times 10 to the 5. Put that in parentheses and square it. and I'm getting 1.3924 times 10 to the 10. I'm just going to do 1.39. 1.39 times 10 to the 10. Already I'm seeing different powers of 10. I'm going to comment on this in a bit. And then 1.63 is the next one. 1.63 times 10 to the 5. If I square that, I get 2.6569. I'll do 2.66 times 10 to the 10. And then the last one is 2.37 times 10 to the 5. Put that in parentheses and square, and I get 5.6169. I'll say 5.62 times 10 to the 10. 5.62 times 10 to the 10. Okay, notice how all of these are times 10 to the 10 except this last one. I can fix this pretty easily by just rewriting this as 0.6625. I'll round it to 0.663 actually. Yeah, I'll do 0.663. I'll rewrite this as 0.663 times 10 to the 10. And you're going to see why I did this in a minute. Now for the r cubed column. So r cubed, we've got, first one is 1.85 times 10 to the 8. And I'm going to cube that. Or you cube and square root it if you choose the other approach that I mentioned. This gives me 6.33 times 10 to the 24. Next one is 2.38 times 10 to the 8. If I cube that, I get 1.348 times 10 to the 25. I might have to do the same thing with this one. Yeah, I think I'm going to change this to 0.633 times 10 to the 25. 0.633 times 10 to the 25. And again, you'll see why I'm doing this in a minute. 1.35 times 10 to the 25. Okay, next one is 2.95 times 10 to the 8. If I cube that, I get 2.57 times 10 to the 25. 2.57 times 10 to the 25. And last one is 3.77 times 10 to the 8. If I cube that, I get 5.358. I'll say 5.36 times 10 to the 25. Okay. Now it's asking us plot the graph on the axes below. Label the axes with the variables used and appropriate numbers to indicate the scale. So we need to label the variables. We already did that earlier. T squared on the vertical axis and r cubed on the horizontal axis. By the way, you could have done it the other way around. You could have rearranged the equation for r cubed instead and had r cubed on the vertical and t squared on the horizontal. It's just that in part B, when they told you to find period as a function of radius, they kind of set you up to make t the variable, or something involving t to be the variable on the vertical axis. So they kind of were steering you in that direction, but they never said for part E that you have to exclusively rely on the function that you get in B. Come to think of it, you don't even need to rely on your answer to part B for part C. You could have again, just you could have come to the same conclusion that you need t squared and r cubed, or t versus r to the 3 halves. You could have formatted your linear equation to where r was the dependent variable and t was the independent variable, or the square and cube of them, whatever you wanted to do. Anyway, so they give you a lot of space here, and they expect you to make good use of this space. Don't just cram your entire graph into this tiny little corner. You're going to lose points for that. They want you to try and use a reasonable amount of this space. Obviously, they don't want you to force the graph. They don't want you to forcibly stretch the graph and make it, extend to parts of this graphing section that it doesn't need to go to. But, use a reasonable amount of the graph. And you'll notice, if you calculated your numbers correctly, that they gave you everything you need to make it easy. So they've given you, let's see, if I count from the bottom, I've got 1, 2, 3, 4, 5, 6 bold lines over here. I've got 6 sections, and then within each section, they are divided into 2, 4, 6, 8, 10. I can split this. They're divided into 5 even pieces. You've got the dotted lines occur at 1/5 of each height. Similarly, if you go in the horizontal direction, you've got 1, 2, 3, 4, 5 for each box, for each bold line. And then we've got 1, 2, 3, 4, 5, 6 boxes going to the right. So you want to try and scale your axes so that you can comfortably fit stuff in here and be somewhat detailed. If you cram everything into a tiny space, your detail level is going to suffer. If you try to make things too big, then you're probably getting too bogged down by detail and missing the point of the question. So I'm going to go ahead and try and copy what they have here, and then we're going to compare with the numbers that we've got and decide on an appropriate scale for our graph. I think I might want to get a ruler for this. So it goes 1, 2, 3, 4, 5, 6 up and 6 across. Let me see, it's probably going to be easier for me to do this in centimeters. Oh, what do you know? That's exactly 6 centimeters that I've given it. Okay, so 1 here, 1 here, 1 here, 1 here, 1 here, and 1 here. So those are going to be like my major grid marks. And then over here, I guess I made this a little bit too big. Well, actually no, let's stretch that a little bit. And yeah, over here I'll give 2 centimeters for each mark. So 2, 4, 6, 8, 10, and 12. And let's go ahead and draw these lines. I'm worried that this is going to end up looking wrong. Actually, not looking too bad. Okay, that is not terrible. I'm going to skip on drawing all the minor grid marks or else we're going to be here all day, but you can imagine that they're there. You know, what I probably should have done is just gone to Staples or something and printed off a copy of this exam so that I wouldn't have to draw the graph from scratch, the graphing area, I mean. Aren't you glad you don't have to do this on your AP exam? Aren't you glad that they're just going to provide you the space for it? Oh, and I see I did not give myself enough length on these. Let's see if we can fix that real quick. Okay, that'll do. Okay. So now let's look at the numbers that we have and see what we can do here. So first off, I made everything times 10 to the 10 over here and made everything over here times 10 to the 25. That way I can say that my vertical axis is t squared in seconds squared times 10 to the 10. And r cubed, whoops, didn't give it enough space. And my horizontal axis is r cubed in 10 to the 25 cubic meters. What I'm saying here, by writing this on my axes, by writing these in my axes, I'm saying that each of these is 10 to the 10. In fact, you don't even need to write this here, actually. You don't even need to write it here. Where you would write it is over here. So over here you would write, this is, well, I guess we're about to find out. We've got 0.663, 1.39, 2.66, and 5.62. So it looks like we're going from 0 to almost just shy of 6. Well, how about that? I've got 1, 2, 3, 4, 5, 6 boxes of space. So it looks like this is going to be 1 times 10 to the 10, 2 times 10 to the 10, this one's going to be 3 times 10 to the 10, and I would probably not write each of these. I would probably do 2, 4, and 6, just so that you're not wasting time on the AP exam. And there we go. That is a very nice fit. I will be able to show everything from 0 to 6 times 10 to the 10. And yeah, that's going to fit in there nicely. Okay, let's see if we can do the same thing with r cubed. R cubed, how about that? What a coincidence. It also seems to start somewhere above 0 but below 1, so 0 is going to be our starting point for r cubed, and it seems to go up to, it seems to fit nicely within the range 0 to 6 in multiples of 10 to the 25. So that's going to be 1, 2 times 10 to the 25, 2 times 10 to the 25. Here's going to be 4 times 10 to the 25. And all the way over here is going to be, I don't have the space for it, but 6 times, maybe I can squeeze it in, times 10 to the 25. Okay, that's not legible, and even if it is, it's still horrible. But you get what I'm trying to say here. You would have more space on your AP exam to write this more clearly. So this ensures that we're actually going to use pretty much all of the graph space that we have. That is one thing that they're going to be looking for. If you cramp it all into here, you're going to lose points. Okay, now we can start plotting. So 0.663 comma 0.663, or no, 0.633 rather. 0.663 and 0.633. Well, I've got grid marks within these boxes, right? So this is 0.2, 0.4, 0.6, 0.8. So the 0.6s are over here. And the 0.6s for the vertical direction, I've got 1, 2, 3, 4 of these. And the third one would be the 0.6, right? 0.2, 0.4, 0.6 is going to be somewhere around here. Okay, so that's 0.6 by 0.6. So horizontally 0.633. So a little bit further to the right. And 0.633 is a third of the way between 0.6 and 0.7. Well, 0.8 is over here, 0.7 is over here, and then a third of the way between those would be somewhere around here. And then 0.663 is going to be 2/3 of the way between 0.6 and 0.7. So it's going to be, let's see if 0.7 is there. Okay, so at this scale, it's not going to make that much of a difference. Like, probably at this point, I'm already getting too bogged down by the details and being a little too precise. But the point is, they've given you enough information that you could achieve a pretty reasonable amount of precision. Obviously, it's not going to be perfect because you're not a graphing machine. They don't expect you to be perfect. They don't want you to just completely go screw it and just be sloppy and put together whatever. They want you to make some effort into trying to make this somewhat accurate. They want you to get as close as you reasonably can to what a machine could do. 1.39 and 1.35. I should actually be reading them right to left. 1.35 comma 1.39. So 1.35 comma 1.39. Well, 1.35 is about a third of the way between 1 and 2. So about here, more or less. Yeah, I'm being a little bit more crude now because I want to get this problem over with. And 1.39 is almost at 1.4 in the vertical. So 1, 2, 3. Yeah, I didn't space these correctly, but 1.39 should be somewhere around here-ish. Okay, so that's a point. And then 2.57 comma 2.66. 2.57 is going to be somewhere around here-ish, close to 2.6. So it should be almost touching the third minor grid mark if you're using the graph paper that they provided, the graphing space that they provided. 2.66 is going to be about 2/3 of the way between 2 and 3. So around there. Okay, so there's a point. And 5.36 comma 5.62. 5.36. So there's 5. 5.36 is about a third of the way, so something like that. And then 5.62 is about 3/5 of the way between 5 and 6 over here. So do that, do that, do that. I'm not sure who's calling me, but they'll have to wait. 1, 2, 3, 4. Okay, and it's the third one, so 0.6, a little bit higher than this, but it's not going to make that big of a difference. Okay, given how long they've been buzzing me, I think I know who that is, and I will deal with them later. Okay, so somewhere around here, maybe a little bit higher than where I drew that second line. Somewhere around there. Okay, now we've got 4 data points. Now we can actually draw a best fit line, which is what they asked us to do, I believe. Not yet. So they just said plot the graph on the axes below, label the axes with the variables used and appropriate numbers to indicate the scale. So yeah, putting your t squared here, your r cubed here, and putting numbers on the sides here for all the bolded lines. Well, not for all of them. Every other line is good enough. I would do 2 times 10 to the 10 here, 4 times 10 to the 10 here, and 6 times 10 to the 10 here. And then over here, same thing. 2 times 10 to the 25. Over here, I would do 4. And here, 6 times 10 to the 25. And then F, using the graph, calculate a value for the mass of Saturn. So they expect you to draw a best fit line here. And there are a couple of guidelines. So, first off, we do not know from this information. We cannot infer from the information here that if r cubed was 0, then t squared would be 0. We would expect that from the equation that we got, right? When r cubed is 0, t squared should be 0. I mean, in a perfect world, that's what should happen according to our equation. But in the world of science, you rarely ever get perfection. And so if you were to do this sort of experiment, if you were to do these calculations in a lab, you would probably get some little bit of extra over here. Your best fit line is probably not going to go through the origin. So do not be quick to assume that 0, 0 is an additional free point that you have to have, or that your best fit line has to go through the origin. That would be something I would caution about. Sometimes it is reasonable to assume that if you were doing a different type of experiment where you were doing, like, for example, distance versus time of an object, then yeah, you know for a fact that when the object has been traveling for 0 time, it has traveled 0 distance. You can confirm that with whatever experiment you're doing really easily. You don't really get to observe planets or moons with an orbital radius of 0 to observe that they have a period of 0, right? That's not something that you can actually do in an experiment. So if it was some sort of position versus time experiment over here, depending on the nature of the experiment and how position and time were being measured, of course, you would have to rely on some common sense either way. But yeah, I am not going to try and force this line to go through the origin. I'm not going to try and force it to go through the origin. I'm going to try and find, and use your ruler, bring a ruler, by the way, to the exam. Bring one. And try and see, you're not connecting the dots because they're not all going to connect in one nice line. What you're gonna try and get, and everybody's line is gonna be slightly different. You're not gonna lose points just because you didn't get the exact same line that your friends got, as long as your lines are within a reasonable range. The things they look for are: draw a line that is reasonably close to the data points and have approximately half the data points are going to be above the line and approximately half of them are going to be below the line. And I've got exactly 2 points above and 2 points below. They don't have to be the first 2 points. This is just what I happened to get. Sometimes you might get something where, you know, the first point is going to be below, the next point is going to be above, the next point is going to be below, the next point is going to be below, and then the final point is going to be above, and then your line is going to look like that. Roughly half above, roughly half below, and don't make your line stray too far from any particular point. Because I could, for example, draw, here's another line that, let's do it in, what color do I want? Let's do pink. Here's another line that I could make. Whoops. Kind of bent it at the end, but here's another line I could make. What's wrong with this one? What's wrong with this one, even though I have half the points above and half below, roughly, the points below are really close to the line while the points above are so far away. Look at this distance, look at this distance. That's too much distance compared to these two. You're kind of biasing your line a little too low. So roughly half above, roughly half below in terms of your data points, and try to keep your line reasonably close to as many points as possible. If you have 1 point over here, this one is clearly a bit of distance away from my line, at least compared to these other ones, but it's not that drastic of a difference. Maybe I should tilt my line ever so slightly. Maybe I should tilt it a little bit to make it better. Like maybe something like this would be even better. But that first line I drew is completely acceptable. So once you've drawn your line, what you're going to do is you're going to look for good points on this line to get the slope. Don't try to figure out two random points. Try to pick two good points. There's a good chance with all this graph, there's a good chance that you've got 2 points that are at or very near the intersections of those grid marks, whether it's the major grid marks or the minor grid marks within these boxes. There's a good chance that you have points that are at very convenient and easy to read values. So I would recommend using those somewhere on these major or minor grid marks. I would pick 2 points that are very easy to get the values off of, as easy as possible. Pick those 2 points, do your delta y over delta x, or in this case your delta t squared over delta r cubed, and get that slope. Whatever that slope is, that's going to be equal to what again? It's going to be equal to, we did t squared equals 4 pi squared over gms times r cubed plus, well, we've got nothing there. Technically, if you wanted that plus b, you would just continue your line over here and see where it intersects. And that's just going to be, experimental error, so I wouldn't worry about it too much. The important thing is the slope here, so get your slope and then set that equal to 4 pi squared over gms. Multiply the ms over to this side, divide by slope, so you would get mass of Saturn equals 4 pi squared over g times whatever your slope happens to be. And there you go, you're done with the problem. You're going to get a number that is probably going to be slightly different from your friends, depending on how you round and depending on how you drew your lines, but there is a range. Like the graders know, if people are getting answers between these numbers and these numbers, give them credit. If they went too far outside of these bounds, they weren't being precise enough, they were being sloppy, don't give them credit. Just do a reasonably good job and you'll get the points. Don't fret over this too much. As long as you can show on your paper that you actually know what you're doing, you will be fine here. Now, similar principles apply if they ask you to draw a best fit curve. Let me see, I think it was this one that had a curve. The 2018 Physics C Mechanics. Was it this one? Yeah, they've got like this scatter plot over here. Well, over here they already did the equation. They already came up with a quadratic fit curve. At least they gave you the equation of it. They didn't draw it. Do they ask you to draw it here? Looks like no, they don't. But clearly this is not a line, so if your data points look like they have the shape of a curve and not a line, one, double check your work, just in case it's supposed to be a line. And after you've double checked your work, if it just makes more sense to fit a curve to it, then fit a curve to it. And again, kind of the same idea, half the points roughly above the curve, half below. Try to keep your curve reasonably close to as many points as possible. Don't let it drift too far away. Some of these points you can see just from the way this is going to fit. Some of these points, like this point over here, is definitely going to stay far away from whatever decent curve you draw. This point over here, just, it seems to be the odd one out. But most of the points are going to be pretty close to a curve that you draw along where I'm tracing the mouse right now. If you had to draw a curve for this problem, that is. Most likely they'll ask you to draw lines because you can just use your ruler and get that right. Drawing curves, I think, is a bit too far. I don't know if they've ever actually done that, but I've seen it in textbooks at least. I've seen textbook questions that expect you to draw a curve of best fit. So you never know. They might ask you to do that. If they do, you know what to do. It's not rocket science. Anyway, now that we've done that, what else do we have? So best fit lines we've done. We've talked about all the criteria for drawing a good best fit line and how they will grade you on your line. Drawing diagrams and knowing when to draw them to scale. They might ask you, for example, to draw a force diagram. They might give you something like, here's a table and some pulleys, and here's one mass, and here's another mass, and they'll tell you like M1 is heavier than M2. They'll tell you M1 is greater than M2, and then they'll ask you to draw force diagrams. If you know M1 is heavier than M2, then one, when you draw the force of gravity on M1, M1G versus M2G, they expect you to show that M2G is smaller. Even if you don't know how much smaller, qualitatively at least, you know that it's at least a little bit smaller. And then for the tension forces, the way this thing is going to move, the tension needs to be, well, in order to pull M2 up, it needs to be bigger than M2G. Get out your ruler if you need to. They'll probably give you like graphing space actually on your diagram. They'll probably give you like, here's M1 and here's M2, and then they'll give you like lines, and you can use that to make sure that the lengths of your vectors compare properly. And so you would do what? M1G, I guess I'll draw a third line here. M1G goes this far, M2G only goes this far, and then the force of tension, whether you call it F sub T or T, you'll draw it bigger than M2G. And it should be the same tension on M1, and it should be smaller than M1G. So making sure that your graph scales are correct. If you know the exact scale, then get it exact. If you don't know the numbers ahead of time, then at the very least, if you know for a fact that some of these forces are going to be bigger or smaller than others, show that on your graph. Show that on your graph even if you don't know the exact ratio of their magnitudes. Show what you can. Show what you do know. So that's my commentary on scaling. You'll get the occasional straightforward question on the FRQs here and there. I think you'll recognize those when you see them. I already talked about the importance of reading the solution guides. Did I talk about using an expression when you can't prove or derive it? So they might give you something. We did kind of talk about this, I'm pretty sure, earlier. They might give you a problem where part A or part B, one of the earlier parts tells you to derive an expression, or rather, what they'll say is prove. They'll give you the expression, prove that, I don't know, the speed is given by and then they'll give you some sort of equation, I don't know, 1.5t plus 3 over 6g plus 7, or whatever formula they give you for the scenario that you're presented with. Prove that the speed is given by this. And then the next question will say, what is the speed at time 7 seconds? What is the speed at time 7 seconds? Well, if you couldn't prove this in part B, you can still use it in part C. So go ahead and pick up that free point. If it's just proving a formula that they already gave you, even if you can't find the proof, you can still use the formula. You can still use it to solve later parts of the problem, so go ahead and do that. Don't be afraid to do that. It's more for the ones where they ask you to derive an expression, like from scratch, instead of proving something that they just hand to you. With those, it's a little bit iffy. They may or may not give you credit depending on successful derivation of the expression before using it. And I already talked about justifying things, so they like to say a lot, justify your answer. They'll ask you a question. They'll ask you something like, which of the objects will be moving faster after these two objects collide? Justify your answer. Justify just means explain how you know. You can do it with math, you can do it with words. Sometimes they will specifically tell you to just explain in words without using any equations, like that example we saw earlier today. So, yeah, this is really more English skills than anything else. Make sure you learn the correct vocabulary, make sure you know how to speak the language of science. Don't be afraid of sounding like a nerd. I'm certainly not afraid of it. And look where that got me. This could be you. Okay, maybe that's not the best incentive to give people. And then the last thing. Last thing is the curveball question. They might present you with something new, and you need to be able to grapple with that. This is common in the world of science, right? Imagine you're a scientist, you're a researcher, you're working on your thing, and then you go through the scientific journals and you find somebody discovered something that you might be able to use for whatever you're researching, but you weren't there with them. They came up with this new thing that you've never heard of before. It wasn't in any of your previous courses that you took to get your master's degree or whatever. it's a new thing. It just got published, and you need to be able to read that paper and understand what is the paper about, what was the experiment, how did it work, how did they figure out whatever it is they figured out. And of course, if you think there's something wrong with their experiment, be able to spot that and make an argument and prove them wrong. Maybe do your own experiment and try to discredit theirs. So you might get that occasional curveball question. One in particular, where was it? Here we go. So here's one in particular that comes to mind. The 2011 free response question number 3 for mechanics. And to those of you who are in Physics 1, I hope you realized early on that even though these have been Physics C questions that I've been looking at, the ideas that we've been discussing are still relevant for your Physics 1 exam. Anyway, over here, question 3 from the AP Physics C 2011 exam. It says, let me zoom in on it a little bit. It says, the torsion pendulum shown above consists of a disk of rotational inertia I suspended by a flexible rod attached to a rigid support. When the disk is twisted through a small angle theta, the twisted rod exerts a restoring torque that is proportional to the angular displacement, where beta is a constant. The motion of a torsion pendulum is analogous to the motion of a mass oscillating spring. So this was actually my AP exam when I was in high school, and I had this one. He wasn't my classmate in AP Physics because there were 2 AP Physics classes, and he was in the second class. I had him in my AP Calculus class, though. He lost his mind over this question. After the exam was done, he would not stop complaining about it. He thought it was stupid, he thought it was unfair, but if you look at the question and just read it carefully, they're telling you the motion of a torsion pendulum is analogous to the motion of a mass oscillating on a spring. So this is the rotational version of a mass spring system. And from there, you've got, well, torque equals a negative constant beta times theta. This is similar to a force being equal to a negative constant k times x. This is similar to the format of the spring force equation. And based on that alone, you would be able to do, which one was it? Part B. Part B, using the analogy to a mass oscillating on a spring, determine the period of the torsion pendulum in terms of the given quantities and fundamental constants as appropriate. They're literally telling you, using the analogy, they're literally telling you to just say, hey, this equation looks like this other equation for the thing I do know, so just pattern matching, here's what you're supposed to get. And then from there, oh, how about that? This is another best fit line problem. I didn't remember that part. I just remembered I won't say his name, freaking out over this problem and complaining that it's unfair. Let me see, what does part A say? Oh, and over here, for you Physics C students, I kept on telling you this was a thing if you didn't believe me. It says right here, in terms of quantities given above, write but do not solve the differential equation that could be used to determine the angular displacement of the torsion pendulum as a function of time. A lot of write but do not solve differential equations. For second order differential equations, like the type you see in simple harmonic motion problems, like I said in the previous stream, they're never going to ask you to solve a second order differential equation. You don't have the calculus know-how to do that. I mean, I kind of explained it to you already last time. It's pretty simple, at least for this specific format. But even so, at that point it's turning into a calculus exam, and they already have an AP calculus course, so go take that test instead if you want to try and solve differential equations. And even then, AP calculus doesn't make you solve second order differential equations either. Okay, so now that that is done, I believe that should be pretty much everything. Let me think. Oh, right, exam scoring. Last thing, a mini rant, I suppose. So you may have heard some people saying you only need 55% to get a 5 on the AP exam. This is not entirely true. I'm going to call it the 55% lie. This is not entirely true. So there used to be a time, once upon a time, where they would tell us what percentage score translated to a 5 or a 4 or a 3 on the AP exam. Well, they don't do that anymore because people started to game it, I guess. That would be my assumption anyway. Because people started aiming low. People started going, oh, I only need this percentage to get a 5. And the students weren't actually doing what they were supposed to do, which is actually care about and learn the material. They were more fixated on scoring on the test, dumping all their knowledge on exam day, and never thinking about the subject ever again for the rest of their lives. Not good. I'm not the biggest fan of College Board, but at the very least, I hope, anyway, they have the right intention with concealing this information nowadays. But yeah, 55% was, I think, the latest one that they published before they stopped publishing this information altogether, and that kind of just stuck with people. There's this article you can find online that lists this, and people just took it as fact because it's the only thing that pops up when people Google what percentage needed to get a 5. But it changes from year to year. It changes from exam to exam. Back when I took it, I was told that the students from the previous year got 5s if they scored 65% or higher. So it moves back and forth. And the way they decide this cutoff, it's not graded on a curve, as many people would have you believe. It's not graded on a curve. So if you have a bunch of classmates that are going to perform poorly, that is not going to help you. That's not going to curve you up. If you were banking on that, not going to happen. The way they do it is they write the exam questions that they intend to use for the year, and then they slip those questions into the exams of actual college students taking the actual college version of that course. And then however the professors grade them on those questions, and however the professors decide who's getting A's, B's, C's, D's, whatever, College Board goes based off of that. They probably adjust it a little bit and go easy on you because you're high school students, so they probably make it a little bit more gracious. Maybe the professor puts the cutoff at a 70% and College Board gives you, okay, 65% is good enough since you're high schoolers. Maybe. Not those exact numbers, I'm just throwing numbers out there. They do whatever it is they do, and they decide what that cutoff score is ahead of time. It's based on the performance of college students that you've never known and never met, and they don't know, by the way, that they're getting AP questions. They just get 1 or 2 mixed in with their regular exams, and they have no clue that this is part of the process. So if you have siblings in college and you think you're going to get the questions from them. It doesn't work that way. They don't even know that they're involved in this. So yeah, cutoffs are predetermined, and they're not based on your class. They're based on the performance of college students that you've never met and were never aware they were doing an AP exam question. So don't believe anybody who tells you you only need 55% to get a 5 on AP Physics C Mechanics. It is a lie. They do not know. Maybe it's 55% one year, maybe it's 65% another year. Maybe they wrote an exam that was particularly easy one year, and a lot of those college students scored really highly, so the standard is raised and you need an actual 80%. And you might say, well, that's ridiculous, jumping from 55% to 80%, but if it really is that much easier, then that should be achievable for anybody who would have scored a 5 on the previous harder exams. So at the end of the day, just try and score as many points as you can and demonstrate as much knowledge as you can. Learn as much as you can. If you haven't learned all the material yet, try and get caught up on that. Try and learn things thoroughly, especially force and rotational dynamics. When you try to learn those two thoroughly, they should drive you back towards those earlier chapters. Like you get stuck on a force question or an energy question, and that makes you go back and read up on something that you probably haven't quite mastered yet in force or kinematics. That would be the process for me. I would first of all go through everything in order, then go back and focus, hyperfocus, force and rotational dynamics, and then those questions, as you practice them, will naturally lead you back towards the other chapters, except maybe simple harmonic motion. That one's kind of detached from the rest a little bit. I mean, I guess it's kind of connected to the energy chapter in some ways. Yeah, it would lead you back to energy, if nothing else. And I think that is it for the AP exam overview. Now, something I promised several streams ago, I finally played around with it and figured it out. This will be the last thing before we wrap up. Some of you might remember from simple harmonic motion, there was a question that I tried to explain how you figure out the change to the period equation for a pendulum in an elevator, a simple pendulum in an accelerating elevator. And I kind of went with the hand-wavy explanation because I couldn't quite remember how I used to explain it before. But now I believe I have it. So let's say this elevator is accelerating upward. I'm going to call this AE, acceleration of the elevator. Okay. So normally, when there is no acceleration, let me draw the pendulum again, just standard pendulum, standard situation. Normally, you're going to have, of course, just whatever your normal tension force is, whatever your usual weight is, mg. And in trying to prove that this was simple harmonic motion, I used a coordinate system where I had one axis going tangent to the path that this pendulum would take, and another axis going basically along the string. This time I'm not really going to do that. This time I'm going to stick with the traditional X and Y coordinate system. This time I'm going to stick with this. So we know when you pull a pendulum back, it starts with 0 speed. And if it has 0 tangential speed, then it also has 0 centripetal acceleration. But that doesn't mean it has 0 acceleration. It just has 0 centripetal acceleration. It's still got to have some acceleration because it starts from rest and it ends up moving. And also it ends up moving in 2 dimensions. It ends up moving, if I release it from here, it moves down and it moves to the right. So it does have some acceleration in the horizontal and vertical. And those accelerations are changing, of course, as you go. We know that acceleration for a simple pendulum, this is going to be the total acceleration, is a function of time. And it'll be negative a omega squared cosine of omega t plus phi if you start with x equals a times cosine of omega t plus phi. Or you could have it as a sine function. It doesn't matter. The point is it's going to go up and down as a sine or cosine function. The point is it's going to be variable. It's a variable acceleration. Your total acceleration is variable, and therefore your acceleration in x and y are also variable. But the important thing here is that they're not 0. The thing to remember is that they're not 0. Not 0. So if I were to just write an expression for any moment in time for this pendulum, I would have, let's see, its vertical component is going to be touching this angle theta, so the vertical component of the tension is going to be force of tension cosine theta, and the horizontal component is force of tension sine theta. So I'm going to do force of tension sine theta. That's the only force I have in the x direction. That's going to be the mass times the acceleration in the x direction. Okay, what about in the y direction? In the y direction, I would have the acceleration in y is going to be force of tension cosine of theta, which is going to point upward, minus mg, which is pointing downward, and that's going to be equal to mass times whatever the acceleration is in y. These, again, are both variable. They're going to be components of this. Okay, so that is the standard scenario where the elevator is not accelerating. What about the accelerating elevator scenario? Well, in order to have this upward acceleration in addition to whatever acceleration keeps this pendulum swinging, the force of tension needs to change. The rope or string is going to have to pull tighter in order for this to work. So I'm going to have a new force of tension. I'll call it force of tension star. I'll call it force of tension star. Whatever it adjusts itself to, force tension star, whatever it adjusts itself to, that's what I'm calling it. I'm calling it force of tension star. And then you still have the same mg downward. So let's see what we have this time. So this time we've got force of tension star times sine of theta equals mass times acceleration in x star. It's not going to be the same acceleration in x. It better not be because, well, the question that asks you what happens to the period of a pendulum in an accelerating elevator, the expectation is that the acceleration changes, like this acceleration, the pendulum acceleration is going to change. The period and frequency are changing, so this a of t must be changing, which means both the x and y components of a of t must also change. So this is going to be a different acceleration from this one. And then similarly, I'm going to write force of tension star times cosine of theta minus mg equals the mass times, you've got two different kinds of acceleration in y here that force of tension star times cosine theta needs to supply. This time the force of tension needs to do both the work of causing the simple harmonic motion, providing the y component of that motion, plus just the new raw vertical motion due to the elevator. So this is going to be equal to the mass times the ay star. This is going to be the y component of like the pendulum acceleration, the acceleration that causes simple harmonic motion, plus the acceleration of the elevator. If I distribute this and subtract mass times acceleration elevator on both sides, I get, so starting from here, we get force of tension star times cosine theta minus mg, and then minus ma elevator equals mass times ay star. If I factor out the negative m from here, I get force of tension star cosine theta minus m times g plus the acceleration of the elevator equals ma star. Okay, so now if I take this equation and this equation, what I essentially have is the x and y components of the pendulum acceleration under a different tension force, and it's as if the object has a different weight adjusted by whatever the acceleration of the elevator is. So it's as if the elevator accelerating upward is increasing the gravitational force. This is kind of similar to, at least up over here, when I added these two accelerations. This is kind of similar to what happens when you have accelerated circular motion. When you have an object that is in circular motion and stays in circular motion, but is accelerating. So in addition to a centripetal acceleration that's changing, you also have a tangential acceleration, and then your total acceleration is going to be, you do Pythagorean theorem and combine the two. This is kind of the same thing that I did over here, except I didn't need Pythagorean theorem because whatever the y component of the simple harmonic motion part of the acceleration is, well, it's a y component, so it can just add directly with an acceleration that's directly along the y-axis. So that's my justification for doing this over here. I forgot to mention it earlier. But yeah, this, if you just compare these two formulas, well, this one doesn't really tell us anything of significance here, but this one does. This one tells us that it's as if you have a new tension under a new acceleration due to gravity, g plus ae. And of course, if the elevator was accelerating downward, this would just be a negative value that you plug in. So it would still be plus, it's just plus a negative. But yeah, there you go. That's the pendulum in an elevator question addressed. You're not going to need to do this proof. If they ask you about this at all, they're just gonna ask you to kind of give the intuitive reasoning that if the elevator is accelerating upward, then it feels as if everything inside the elevator is heavier by m times whatever that acceleration is. You probably could have inferred this on your own just without doing any calculations. You probably, going by your gut, would have arrived at this conclusion anyway, but it's nice to have at least some sort of math to justify it, or at least pseudo-justify it. But that is it. That is now everything that I needed to cover for today, and that is the true end of the course. I might release a random video here or there on a particular problem or two if I feel the need to. But otherwise, this is it for me. For other courses, what do I want to do for next year? I haven't even decided yet. I'm not sure if I want to do anything for next year, but I've had some suggestions from some of my students, and one in particular thinks it would be a good idea for me to do like a computer science course, but that's not going to be an AP course. That's going to be, if I do it, that would be just something that I'd have to format and structure and just make it my own thing. Just make it a course for the sake of learning the subject rather than tying it to a particular exam. I don't know how well that would go, but other than that, the more obvious next places to go would probably be Physics C, Electricity and Magnetism, or Physics 2. Physics 2 isn't taken by that many students, so I'm not sure how worth it would be to do that, but if I decide to do either of those, then I'm gonna have to make sure to start early and not wait until like the end of September like I did with this course, because with this course I really thought that I would be able to just get it all done, just scheduling sessions on Sundays and just one session per week would have gotten me there, but somewhere towards the end I realized I was not going to make it in time unless I did some additional sessions, and then my schedule kind of went out of whack trying to find days during the week instead of just the weekends, and trying to do 2 streams a week where I could, and then having that backfire with the following week having to be skipped or whatever. So yeah, if I'm going to start another AP course, then I'm going to want to start early. But I haven't decided. I'm not promising that I'm going to do any of that. I'm going to think about it. But yeah, those are some of the options. Another AP Physics, a computer science course, or maybe even a math course, like a higher math course. It's been a while since I've touched multivariable calculus. I'm sure some people would like to see that. So maybe I'll touch on that. I did try to start that last year and other things took priority, so maybe I'll make a second attempt on that. Or maybe we'll do linear algebra or differential equations. I don't know. I have options. I have to weigh them and decide what it is I want to do. As for the traditional office hours, for those of you who have missed them, I don't know. I think I'm going to hold off on doing that. I've seen more success with just having some sort of structured course for now. I'll probably have to wait until there's like an audience for the traditional office hours, because it was originally meant to be this sort of come in and ask your questions sort of thing. And that isn't something that you can consistently have happening when you're starting off as a small channel. Who would have thought? So I resorted to just having things planned ahead, and they would always be just kind of random things, and yeah, going with something more structured instead of just having a random topic of the week is probably better for right now. And maybe in the future, if there's an audience for it, we'll get back to traditional office hours. But until then, I'm going to try and survive these next couple weeks of helping panicking AP students get ready for their exams, and then work on some of my personal projects. I've been holding off on this one game review for a bit too long, and I think it is about time that I do it. And then once that is done and sorted out, I'll probably finally get back to doing some game streaming on my Twitch. But that is a concern for like a few weeks from now. The more immediate concern is getting all these students tutored and earning my summer break. So yeah, that'll be it. Hope you enjoyed the course. I hope this last extra part over here proved to be useful. And best of luck on the exam. Study hard. Remember that ignorance is not bliss. That's something that I haven't said in a while. I used to use that as an outro all the time back when I was doing the chemistry series. But yeah, remember that ignorance is not bliss. Always try to learn something new. Don't be one of those people who thinks that learning is icky or whatever. Don't adopt that mentality. That's how societies collapse and die. And yeah, I think that's it. Class dismissed. I'll probably see you next year with something new, maybe. Take care until then.